the next episode of Chemistry. This is a continuation of our last video. This is the sequel to Thermochemistry, one of the only sequels you've been begging for lately. As Hollywood is just really in their bag of creativity and tricks, aren't they? Oh man. What are we going to see next? Who's going to be the next Black Panther? I don't know. Let's get creative, shall we? Let's come out of left field. As always, links to the notes and the slides on your screen can be found in the description of this video. Let's have some fun, shall we? Because Thermochemistry Part 2 is simply a continuation of what we were just doing in Thermochemistry Part 1. We're just going to add a couple of equations and we're going to throw you some new tips and tricks on how to pursue this information. And the first of which is entropy, one of our key terms for today. Entropy. Murphy's Law. Maybe you heard of it? I've never known a single soul named Murphy in my entire existence, all 48 years on this lovely green earth, and I've never known anyone named Murphy, except for from that show, The 100, which of course went very much downhill after seasons 1 and 2. Then it picked it back up, and then it just said, lackluster ending. Watched it all the way through. Can't say I didn't. Can't say I was ever turned away. Never totally spurned by the CW. But hey, here we are. Murphy's Law states that the universe is constantly moving towards disorder. That chaos is just on the other side of a very dimly lit doorway. And entropy is the measure of the disorder of whatever system we are assessing. So if we are constantly gravitating towards this disordered existence, is this why all good things must come to an end? Me, I'm a very passionate Star Wars aficionado, and you know why this little GIF on your screen is so infuriating. If you do, I'm really sorry. I'm really sorry. Moving on. We can assess entropy just like we have our other variables, where we simply take a look at the change that is occurring, the products minus the reactants. But also, we can take a gander at our reactions in a whole new type of way to see whether or not things are getting more ordered or more disordered over time as a reaction is progressing. And so delta S, the change in entropy, is positive when we are getting more disordered, when we are getting less organized, a little more chaotic, right? Cue the Heath Ledger Joker voice here, right? I'm just a dog chasing cars, and I wouldn't want to know if I caught one, right? That's not me trying to do an impression, by the way. I would never try. I would never try. And so, by looking at reactions in this way, we can actually see if a reaction is favoring moving forward or going backwards. That's right, reactions are reversible. Sorry to spoil a few things for you. Not every reaction, but a lot of reactions are. And that's when we throw in a whole new term here known as equilibrium, which is going to dictate a huge chunk of AP chemistry in the future. But for now, we're just going to mention it in just very brief detail in this video, and we'll give it its proper focus a little bit later on down the line. And so when I'm assessing entropy values, yes, I can do the products minus reactants, or I can take a look at a few namesake changes that are very, very common in reactions, such as phase changes. Well, when you were studying how these states of matter are organized, solids versus liquids versus gases, we all know that solids have a very rigid arrangement of molecules, liquids a little bit less than such, and gases, of course, chaotic, bouncing off the walls, getting as far apart from each other as possible. So gases are the most entropic state of matter, whereas solids are the least disordered. And so if I ever see a simple phase change, such as going from liquid to gas, this would be a positive change in entropy, a positive delta S, because we are going from a more ordered state to a less ordered state, liquid to gas. And of course, if we are freezing, right, or if we are condensing, going from gas to liquid, well, that would be a negative change in entropy because we are becoming more ordered. That is what we are looking at here. But what about if you are forming a solution or forming a precipitate in this case, such as the net ionic equation on your screen, silver ions, iodine ions becoming silver iodide? Well, this is two separate entities becoming one entity, right? I feel like this is pretty logical. Going from two places to one entity, well, that's becoming more organized. Therefore, this would be a negative change to our delta S because we were becoming more ordered than we were before. But what about when multiple moles are coming into play? This is going to be very important for conversations we have a little bit later on. We've got this equation on our screen. We've got 1 mole of C2H4 plus 2 moles of oxygen reacts to form 2 moles of CO2 and 2 moles of H2O. 3 moles of gases forming a total of 4 moles of gases. More pieces equals more disorder, more chaos, more disarray, because there's more possible positions for these pieces to be in. Therefore, this is going to be a positive change to our entropy here, a positive change to our delta S, because we are becoming more disordered. Voila. But of course, we can calculate it the exact same way we've done several of our other variables when we are given standard values here. Notice the units here are joules and Kelvin and moles and all that, but most importantly, joules is what I'm looking at here, and that's going to come into play here in just a second. And so if I'm going from liquid to gas, well, all I'm going to do is take the gaseous product, that's the 188.7, and subtract the liquid reactant, that's 69.9, because it's products minus reactants in order to get the delta S of this change. Pretty basic example and very similar to things that we've done in the past. But now we're going to see where we apply this, and this is what the biggest topic of today is, and that's Gibbs free energy. Delta G, aka whether or not a reaction is spontaneous. The law of the universe is moving towards disorder. The law of objects is to get into positions of lower energy. And it is the relationship of these two that will determine whether or not a reaction will happen on its own. A reaction is spontaneous when I don't have to push the rock down the hill. If the rock was going to fall down the hill on its own, that is a spontaneous reaction. Whether or not the reaction or process occurs without outside influence or input of energy, that is what is dictating whether or not something is spontaneous. And we're going to get an equation for this here in just a moment, but what we're looking for is whether or not, or what the sign our delta G is. Delta G is negative, that means the reaction is spontaneous, aka thermodynamically favored, is the fancy jargon nowadays. Of course, we had to change that, right? New decade, new chemistry. Can't keep anything the same. I just want some consistency around here, okay? I just want some consistency around here, Linda, okay? If delta G is positive, then the reaction is not spontaneous, aka not thermodynamically favored, and therefore needs a little from us on the outside to make it happen. And if delta G is at 0, then that means the reaction is at equilibrium. Well, we're going to talk more about equilibrium here in a second, so I don't want to jump the gun there. But our next equation here, the Gibbs equation, delta G is equal to delta H minus T delta S. A little throwback. Remember, delta H is the change in enthalpy, aka whether or not heat is being released or absorbed in order to make a reaction happen. So this paragraph is very important. This paragraph is very important. This is a very conceptual unit. Yeah, there's equations here. There's, of course, some quantitative analysis to be done with questions and concepts related to this, but this is a very conceptual unit. And this equation is what a huge chunk of the AP test can revolve around, both multiple choice and free response sections, as we're going to come to see at the end of this video. So this is going to be me just repeating what I said just a few moments ago. The world moves towards low energy and more chaos. Which means this reaction, this equation that we're looking at, delta G, is a relationship between the two. The energy versus the disorder. And of course, temperature is going to play a role here because we're looking at states of matter, we're looking at pressure, all these things come into play when we're looking at disorder here. And so the Gibbs equation is delta G is equal to delta H minus T delta S. Incredibly important equation. So let's throw it into the mix here. What if we're just given an equation, right? We're looking at 2 moles of gas, 1 mole of gas makes 2 moles of gas. So if we're assessing it in the way that we just did, this doesn't look to be favoring, this doesn't look to be a entropically increasing reaction. I've got 3 moles of gases becoming 2 moles of gases. That would be a negative change in entropy, which is reflected in our delta S value. So already we have a new way of thinking about reactions. But they also provide us the delta H, negative 120 kilojoules per mole. So this is going to release energy, meaning that this reaction in terms of the thermo side of things is very good, because this means whatever we are becoming is releasing the energy, aka going towards a lower energy state. And yet, in terms of the disorder, it's actually becoming more ordered. So we've got these two variables that are battling each other in this equation. The one thing to note here is we've got our delta H, our enthalpy in kilojoules, and our delta S in joules. We have to convert those, and typically our energy is looked at in terms of kilojoules. So usually if you're looking at practice problems online, you'll see them convert the delta S to kilojoules by just dividing by 1,000, which is what I did here. And so our equation, of course, once again, is delta G is equal to delta H minus T delta S, and we're simply going to plug and chug. We've got the delta H is negative 120 minus the 290, that's the T, times the newly converted delta S, 0.150, to equal negative 77 kilojoules. So this is going to be a spontaneous reaction, a spontaneous process, specifically at this temperature. Because temperature can go up and down and left and right, that means reactions and processes can be spontaneous at certain temperatures. And you think about this, and this makes a whole bunch of sense. Because water melts when the temperature rises above 32 degrees Fahrenheit or above 0 degrees Celsius. It is not natural for water to melt below that threshold. And yet, it is physically possible. But I just have to force it that way. I have to force it to occur. It is not thermodynamically favored. It is a non-spontaneous reaction, right? This is the argument for when your mom or your dad is forcing you to pick up your room. Come on, mom, dad. You want me to resist the universe, man? The universe favors disorder, man. You want me to fight the universe, man? Nah, man. Nah. If you want my socks off the ground, Linda, you're going to have to get down there and pick them up yourself. Right? That's going with the flow. That's how we do it. But if that means that certain processes can be changed, whether or not they're spontaneous or non-spontaneous at certain temperatures, can we assess it with this large table? Well, this is kind of cool. This is what I mean by thinking of this conceptually. The reaction, once again, is delta G is equal to delta H minus T delta S. These processes have fixed delta H's and delta S's. It is the T that can change, and therefore determine where delta G is going to lie, on which side of 0 it's going to lie, the positive side or the negative side. Well, if you've got this negative sign in the middle of this equation, this is very important, because that means anytime your delta S is going to be negative, aka anytime it is becoming more ordered, this negative is going to turn it positive, and then you just get delta H plus whatever this T delta S value is. That's thinking about it. It is numerically, yes, but this is a conceptual line of thinking here. And so if my delta H is negative and my delta S is positive, that means I'm going to have a negative minus this value here that is going to go from positive to negative because of this minus sign in front of it. Well, what does that mean? That means you are always going to have a delta G value that is negative. There is no situation, there is no temperature, as we are always in Kelvin, so we can't go to negative, right? We are always above 0 whenever we are in the Kelvin scale. That means there is no scenario in which the delta G is not negative, and therefore there is no situation in which it is not spontaneous. That is what we are thinking about here. Conversely, if we flip this, if delta H is positive and delta S is negative, that means you've got a positive minus a negative, which is going to become positive. That means there is no temperature in which delta G ever goes below 0. So that means it will always be positive, and therefore this process will never be spontaneous. The things get funky whenever your delta H and delta S are matching signs, right? Notice that when they were opposite signs, we could hit these thresholds where they were always spontaneous or never spontaneous. But when they are both positive or both negative, That's where the temperature plays a critical role. A critical role. Let me go ahead and make that a little more pretty there for you, right? So, if I've got a positive delta H and a positive delta S, well, then the temperature needs to be, or if the temperature is low, then that means this reaction will not be spontaneous. Why? Because this second half of the equation will not be enough to put delta G below 0 if my delta H is positive. But if the temperature gets higher and higher and higher, aka contributing more to the disorder, then that is where it is able to take it into the negative region for delta G and therefore make this a spontaneous process. This table is handy to memorize, but if you can think about it conceptually and you can visualize that equation and plug in just hypothetical numbers and values for it, then it's very easy to go through. I like this sentence down here. I think I worded it pretty well if I do say so myself. When temperature is low, the enthalpy, aka the delta H of the reaction, is dictating the spontaneity. Whereas when temperature is high, it is the disorder that primarily dictates the spontaneity. Remember, heat is going to be released or absorbed no matter what. The reaction has a fixed amount of heat that is going to be released or absorbed. But the disorder of the reaction is contingent upon how chaotic the molecules and atoms are, how much kinetic energy, how much pep in their step that they've got. So, the higher the temperature, the more the disorder is going to play a role in this equation. Very, very important to understand. And our final equation here, or final equations we're going to look at here, small relationships. We've got delta G naught is equal to RATLINK, and delta G is equal to delta G naught plus RATLINK Q. Oh my gosh, what are these new variables? K's and Q's. We'll talk about that here in a moment, but R, a little throwback here to gases. In honors chemistry, we had the ideal gas law constant, Pivnert, if you recall. But R had all these values associated with pressure. But if you will recall, there was a fourth value of R that was related to energy, which is what we are going to use here. And that value is 8.31 joules per mole Kelvin, right? And so we've got our values here. We are able to calculate delta G, aka the spontaneity of the reaction, based on the ideal gas law constant, the temperature, and this natural log of the value K. And Q is effectively another way of looking at equilibrium, which is K. But first, let's define it. What the heck is this? I've mentioned it like 4 times in this video. What is it? Well, it's going to get its own unit in AP chemistry. So why spoil all the fun before we actually get there? Equilibrium is where a reaction actually wants to sit. And what that means is that there are equal amounts of reactant and product being formed at that time. Meaning there's net no change in the presence of reactant or product over time. Once it gets to equilibrium, I got the same amount going this way as I do this way. Right? There's no net change. As much going in as there is going out. So reactions are reversible. That's going to blow our minds here, people. Reactions are reversible. But depending on how thermodynamically favorable a reaction is, will dictate whether or not a reaction wants to go towards the products, aka forward, or reverse towards the reactants. Very important. And the equilibrium constant, which is K, very simply put, is the concentration of products over reactants. That's how you calculate equilibrium. And there's a number of different ways to do it, a number of different variables you can do it with. But it is products over reactants, concentration of them. Very important. Q, what we were looking at just a little bit ago, Q is specifically the concentration of the products over the reactants at any given point in the reaction. So we're not actually at equilibrium yet, we're getting there. So Q can change, K cannot. K is a constant, the equilibrium constant, and that's a very important distinction. However, they never they're never going to change letters like that in equations to throw you off, so you don't have to worry about, mixing those up. K is a constant, very important. And so we can think about this conceptually as well. If it's products over reactants, and this is concentration, aka the amount of which that is present, think about what values of products versus reactants we can have that will yield certain values of K. What if I have more products than reactants? What is that going to do to my K value? What if the opposite is true? What if I have way more reactants than I do products? What is going to happen to my K? Well, if you've got a big number on top and a little number on bottom, that is going to yield a larger number for K. If you've got a smaller number on top than you do on bottom, then that is going to yield a... Hold on. I want to make sure I get this straight. I've said a couple things on these videos completely backwards. I think I nailed that, though. I think I nailed that. We're spitting a lot of words at you. If I've got a large number on top, small number on bottom, that's going to result in big K. And if I've got little number on top, large number on bottom, well, that's going to result in small k, right? Don't get it twisted. Don't get it twisted. That's just how fractions work, baby. And so, let's put some logic here. If the k value is greater than 1, well, then guess what? That means the reaction wants more products than reactants. It wants to make more of the right and less of the left. So that means when we get to equilibrium, we have already made more products than reactants. And at that point of equilibrium, we are making the same amount both direction, but there's a higher concentration of products versus reactants. And of course, if K is less than 1, then the opposite is true. The reaction favors the reactants over the products. And so, if you're looking at the Q value at any given point, which remember changes over time, right? A reaction is not always at equilibrium. It is gravitating towards equilibrium. If the Q is less than 1 and the K is greater than 1, then that means the reaction is going to produce more products. And of course, if the opposite is true, then we are going to make more reactants, aka the reaction is probably not spontaneous because the reactants are favored. It doesn't want to move forward. And this is what leads us into all kinds of cool concepts such as Le Chatelier's, right? Where reactions are changing based on the influences of the environment around it. Pretty cool? Pretty cool. So let's do an example with this. We've got delta G naught for the following reaction at 298 Kelvin, and this is simply assessing a reaction, and usually they'll provide the delta H and delta S values just like they did here before, and we're going to use that good old Gibbs equation here. But also, let's take a look at the reaction. We've got this should say a gas right here, 2 moles of gases making into N2 and 3 moles of H2. So this is 2 moles of gases becoming 4 moles of gases. In terms of disorder, that's pretty favored, hence why we have a positive delta S. But it does appear to be an endothermic change. I have to put energy in order to break up these N and H bonds. So, at what temperatures are we looking at in order to make this a thermodynamically favored process? Well, obviously not happening at 298 degrees, because or 298 Kelvin, I should say, because when I plug this in, it ends up with a positive delta G value of 33.4 kilojoules. Because it is positive, this is a non-spontaneous change. But very simple, especially when they give us the delta H and the delta S, it's very easy to plug it in. But now, let's calculate the equilibrium constant, aka K, for this reaction at the same temperature. Well, now that I've solved for delta G from the last step, where I used delta H and delta S, I now have the delta G necessary to solve for the last remaining variable in this equation. That, of course, is K. So we get our setup here, right? R is our gas law constant, but do remind yourself that the gas law constant is usually given to you in joules. Let me find that here really fast. Up here. 8.31 joules per mole Kelvin. And what we just solved for, delta G, is in our kilojoules. So we do have to convert one of them. Something has got to give. Doesn't matter which way you go, right? So long as they can talk to each other. So in this example, I converted the gas law constant to kilojoules, going from joules to kilojoules by simply dividing by 1,000, multiplying by that temperature, and then eventually what we're going to do is we're going to undo this natural log here. So after I divide both sides by the 0.00831 times 298, we get natural log of K is equal to negative 13.5. And then we are going to undo that natural log and get our equilibrium constant to be 1.4 times 10 to the negative 6. That's a very, very small value, which tells you that this reaction favors the reactants. But didn't we already know this by looking at the delta G value? It wasn't spontaneous at this temperature, which means we don't want to make much of the products. We are favoring the reactants here. So this is simply confirming what we already knew here. This small k value means we like the reactants, we don't like the products. Ta-da! Another relationship, and the very final relationship that I think we're talking about here, is the relationship between temperature and enthalpy and entropy, right? And this is simply a derivation of the reaction we just looked at, of the equation we just looked at. So T is equal to delta H enthalpy over delta S entropy. And so the question is, calculate the equilibrium temperature for this standard reaction. We did it for 298 Kelvin. We saw that it was not favored. So let's see where it would be at equilibrium, aka where delta G would be 0 is the question, which is why this equation works. If delta G is 0 in the previous equation, what would it take? Let's find our original equation. If delta G is 0, how could we solve? My goodness, we're looking for this. If delta G is 0, how do we solve for temperature here? And that is why we get delta H divided by delta S is equal to T here. So it's just a simple manipulation of the algebra here in order to get that. And so we plug and chug it, and we find that 467 Kelvin, a very, very hot temperature, is what it takes in order for this to not be spontaneous, but be at equilibrium, meaning that the reactants and the products are in equilibrium with one another. That's all there is to the second half of thermochemistry from what I can tell. And so let's go ahead and dive into some multiple choice and free response questions. And I want to show you that, yes, while the numbers can be ever present in these questions, this is a very conceptual way of thinking about this material. In which of the following circumstances is the value for K always greater than 1? So let's apply a little bit of the thinking that we've already had here today. When K is greater than 1, and if K is products over reactants, the concentration of products over reactants, that means it wants to have more products than reactants if K is greater than 1. Which means this reaction is looking for something that is going to be spontaneous, meaning the reaction wants to progress towards the product sides. Which values would give us a spontaneous reaction? Well, the equation we're using here is the Gibbs equation. Delta G is equal to delta H minus T delta S. And for a reaction to be spontaneous, I need delta G to be negative. So which values for delta H and delta S will always give me a negative value for delta G? And if you might be memorizing the table from several slides ago, or maybe you're plugging in some hypothetical values in your head, well, for something to always be negative, delta G, wouldn't we need our first variable here to be negative, delta H? Which means right away it has to be C or D. It has to be C or D. The equation is delta G is equal to delta H minus T delta S. That means if delta H is negative, we're off to a really, really good start here. So it has to be C or D. But now, does delta S want to be the same sign as delta H or the opposite sign? And the answer, if you'll recall from a little bit earlier in this video, is it must be the opposite sign from delta H, because it's delta H minus T delta S. That negative sign in the middle is able to flip those signs there. And so we want delta S to be positive there in order to keep the second half of that equation negative, right? A little throwback here. Let's make sure we go ahead and remind ourselves what that equation looks like. Ta-da! If delta S is positive here, then that means the second half of this equation will always be negative because of that negative sign here in the middle. So if this is negative and this delta S is positive, then that means this equation will always, without fail, yield a negative delta G, aka a spontaneous reaction. Hence why our answer is D here. Use the following information. A couple of reactions up here that I grabbed from a review book. We've got some reaction values here, the delta H values here, and we're going to answer some questions. If reaction 2 were repeated at a higher temperature, how would the reaction's value for delta G be affected? So this is once again using the Gibbs equation. Delta G is equal to delta H minus T delta S. How would the value for delta G be affected? And if we're looking at reaction 2, I see a liquid plus a liquid makes a gas, and 3 moles of gas. This is one of the most entropically favored reactions I think I've ever seen. 2 moles of liquids becoming effectively 5 moles of gases. That is chaos, baby. And what did we say? If we elevate the temperature, the more disorder is favored, the more entropy is valued in this relationship that we are assessing here. So this is, we're jacking the temperature up, and this is already an incredibly entropically favored reaction. So it should become more negative, right? This should become a more spontaneous process. So anything that says it's positive, we're going to get rid of. B can never be the answer choice. Could never be. And then D staying the same, well, that doesn't make sense. We know that temperature definitely plays a role in terms of entropy. So why would it ever be D, which leaves us between A and C? They both say it'd become more negative, but let's see what this says in answer choice A. It would become more negative because entropy is a driving force behind this reaction. Well, that's just a very just plain, solid, well-situated answer. Why? Because the equation is delta H minus T delta S. Entropy is ever present in that reaction. Of course it's a driving force. Of course it's a driving force. So let's see what answer choice C is. It would become more negative because the gases will be at a higher pressure. This is true. And pressure is important to chaos, right? But if you're at a higher pressure, doesn't that just force you closer together? And when you're closer together, doesn't it mean that I am better able to predict where you're going to be? AKA, you are more ordered? Huh? That doesn't sound like chaos to me. That sounds like I know exactly where you're going to be. So whereas, yes, the pressure would increase due to a higher temperature, that's not the relationship that we are looking at here. The fact that the temperature is being jacked up and this reaction, the equation itself at higher temperatures means entropy is more favored. A is absolutely the correct answer, and there is simply no debate on it. So let's answer a couple more questions associated with these same values here. Under what conditions would reaction 3 be thermodynamically favored? We've got reaction 3, which is 1 mole of gas and 3 moles of gas becomes 2 moles of gas. That is not favoring disorder if we go towards the products. This is 4 moles of gas on the left becoming 2 moles of gas on the right. That is becoming more ordered, meaning that the delta S is negative here. But the question is, in what conditions would reaction 3 be thermodynamically favored? That means we need delta S to not dominate this process. The delta H is already negative, which means if T and delta S were out of the picture, the fact that delta H is negative means delta G would be negative. So I need delta H to be the dominant factor here. And let's go back to this sentence that, man, I feel like I just expertly crafted for you guys. Let's go back here. When the temperature is low, it is the enthalpy of the reaction that primarily dictates spontaneity. Whereas when the temperature is high, it is the disorder, the delta S, that primarily dictates the spontaneity. So yes, you could memorize this table. That'd be lovely. Or if you understand what we are looking at here, the equation in and out. And when I'm changing the variables it can change, which of course is temperature, we want delta H to be dominant here. We want delta S to be irrelevant here, which is why the answer is going to be favored at low temperatures. The answer is C, favored at low temperatures. It can't be always favored. It can't be never favored. We can already see that the delta H is negative here. The answer has got to be C or D, so at least it's a 50-50. But the answer is going to be C here because we need the delta H to be the dominant force here. Now number 4 here, and let me crane my head out of the way. If 64 grams of the CH4O were to decompose via reaction 4, approximately how much energy would be released or absorbed? And this reaction actually has nothing to do with this unit. I like to throw these questions in here every now and then where even if you are lost on a unit, you can still get questions right on these sections of your tests, right? Because we're constantly recycling information that we've already covered. It's very important to understand that stuff doesn't go away just because you moved on to the next thing. So 64 grams of CH4O. First of all, let's take a look at reaction 4. Reaction 4 is a negative delta H, negative 65 kilojoules per mole. That right away should tell us that that is energy being released because it is a negative value. This is an exothermic change, which is why we can already eliminate some of these answer choices. A is 65 kilojoules of energy will be absorbed, an endothermic process. C is 130 kilojoules of energy will be absorbed, an endothermic process. Right away, A and C are gone. B and D are the only possible answer choices. So let's see how we narrow that down. If 64 grams of CH4O were to decompose, this is the amount of energy released from 1 mole of CH4O. So what I need to do is I need to find out how much 1 mole of CH4O weighs. Well, that's 1 carbon, which is 12 grams. That's 4 hydrogens, which is about 4 grams. So 12 plus 4 is 16. Plus another 16 from the oxygen is about 32. And oh, convenience! 64 is 2 times 32. which means this 64 grams is the decomposition of 2 moles of CH4O, which means I'm going to take this value and I'm going to double it. So the answer is D. 130 kilojoules of energy will be released. Simple. Piece of cake. Let's move on to our one and only free response question on this video. This is going to be a shorter one, right? We like that. The standard free energy for delta G for the reaction above is negative 801 kilojoules per mole at 298 Kelvin. And we've got a bunch of bond dissociation energies, which is something we covered in Thermochemistry Part 1. So if you want to throw back to that, then take a look at the first part from this video series. Use the table of bond dissociation energies to find delta H. So we're finding the change in enthalpy for this reaction, which means we are going to use an equation that should look very familiar to us. Bonds broken minus bonds formed, right? A very, very common concept utilized on a free response section of AP tests. Very, very common, where you have to account for not only the bonds that are present, but how many of each bond is present, which is why the coefficients and the number of bonds within each entity is very, very important. Because in CH4, there are 4 carbon to hydrogen bonds. And if there are 2 O2s, well, in an individual O2, there's a double bond between 2 O's, right? But there are 2 of them. So that means there are 2 double bonds to worry about that I have to break. So that is 4 CH bonds and 2 double O bonds that I have to break. And I am making 2 C to O double bonds. And I'm making as well 4 hydrogen to oxygen bonds, which is why we see the math that we see here. So not only we are accounting for the coefficients, we're also accounting for the number of bonds within each individual molecule. And when it's all said and done, bonds broken minus bonds formed, we get 800 kilojoules per mole. Very important, take note of those units in that table, kilojoules per mole. And the question is, how many grams of methane must react with excess oxygen in order to release 1,500 kilojoules of heat? This is very similar to the last question we just looked at, right? This is the amount of energy released. This reaction, based on the coefficients here, remember it establishes the mole ratio. This is 1 mole of methane, the molar heat of combustion. So for every mole of methane, it releases 800 kilojoules per mole. So if I take the intended amount of energy here, which is 1,500, and divide by that 800, that is going to tell me how many moles of methane I would need. But the question wants grams. So from there, it's very, very simple. 1,500 divided by 800 is 1.9 moles of methane. And then if I take 1.9 multiplied by the molar mass of methane, which of course is carbon plus 4 hydrogens, which is about 16.04 grams, give or take, then that gives me a mass of methane needed to be about 30 grams. I think you get like 30.4 or something like that, which rounded to sig figs here is going to be our 30 grams. Pretty simple, right? Using the parts that we developed in Thermochemistry Part 1 from this video series, and now we're going to apply it to the new stuff, right? What is the value of delta S for the reaction 298 Kelvin? Well, this is actually a different direction from what we did in our examples in this video, and that's one of the reasons why I threw it in here, is we solved for delta H in part A. They gave us delta G here, so now we are going to use those 2 values to solve for delta S. The equation is delta G is equal to delta H minus T delta S. They also told us that the temperature is 298 Kelvin, so very, very easy. Plug and chug, and we get that our delta S is equal to 0.003 kilojoules per Kelvin, or if we convert that to joules, which is the very common unit for delta S, then that's just 3 joules. A very small amount of energy, but positive, right? And it's very small. It's very close to 0. Very close to 0. And part D is one of the coolest questions about this because I think it really illustrates your understanding of the variables that we are talking about here for why this value is what it is. I like that question. I like questions like that. That makes you think about, you know, what the actual cause behind this. We can all plug and chug into equations, but there's more to this set of concepts than just plugging and chugging. Give an explanation for the size of the entropy change found in part C. Man, I really don't know how you would explain yourself if you got the wrong answer in part C, or, you know, you might get the wrong answer in part C because you actually did part A incorrectly. Because part C, it ends up just being the numerator of the equation is negative 800 plus 801. So that's 1 divided by 298. That's why the number is so small. But obviously, if you get wrong answers in previous parts, then your answer to part C is going to be wrong. You can still get credit for that. If your answer in C is right based on wrong information, then you'd still get points for that. But that does make D a little more difficult. But what does it mean when the entropy value is close to 0? What does it mean when the entropy value is close to 0? That's the question you have to ask yourself right now. We know what it means for the delta S to be positive. We know what it means for the delta S to be negative, but we haven't really explicitly mentioned what it means for it to be close to 0. A positive value to delta S means we are increasing the disorder. A negative value means we are becoming more ordered, but this is effectively 0 joules per Kelvin. This is almost no joules. We ain't keeping the lights on with this. And you want to see why? I've got 1 mole of gas plus 2 moles of gas on the reactant side. 3 moles of gas. And it makes 1 mole of gas plus 2 moles of gas. 3 moles of products of gas. 3 moles of gas in the beginning, 3 moles of gas in the end. The order has effectively not changed. The identities, yes, have changed, which is why there's a little bit of non-zero-ness about our delta S. But effectively, we are the same order or the same amount of disorder as we were in the end as we were in the beginning. And that is the explanation for the near 0 value for delta S in this question. So, a pretty quick video compared to what we normally do. Doesn't that feel nice, right? Thermochemistry Part 2, it really felt like that Part 1 was 75% of it, and this was about 25% of it. Maybe even less. Who knows? But this has been Corona Chemistry. The best service that you can get at home to fulfill your chemistry needs. And we hope you tell your mothers about us. We really do. Have a good night.